Section 8.3 is about exponential functions and their graphs. And the first two videos will talk about those things in the abstract. And then the remaining sections are applications, or the remaining videos of this section. So first we have a definition of a basic exponential function, which is f of x equals a to the x. Okay, a has to be between 0 and 1 or between 1 and infinity. And there's a reason for that. If a is negative, see, x is supposed to be any real number. If a is negative, then say a is negative 1 and x is 1/2. Well, now you have a square root of negative 1, which we know is okay, but we're trying to stick with real numbers now. So we want our f of x to be a real number. It's what we call a real function. Real inputs, real outputs. And so that's why we eliminate negative values. Now 0 you don't have, because 0 to any number other than 0 is 0, and so that would be a horizontal line. 0 to the 0 power is what we call indiscriminate. It's undefined, only worse. And so basically that would be with a equals 0, you'd have a line with the x-axis with a hole at the origin, which we don't want to call an exponential function. Exponential functions have certain properties that they share that aren't shared by a horizontal line or any other line. So that's why it has to be a has to be larger than 0. A can't be 1, because if a were 1, you'd have 1 to the x, and that would be 1, which is a horizontal line, y equals 1, and we don't want horizontal lines. But it can be any other real number. A is called the base, and people often use a b. I think I used an a because the book did, or I just used an a. It doesn't matter what you call it. It's called the base. X is called the exponent. Okay, so the exponential function is one where the variable is in the exponent. Right. So the base of an exponential function is a constant, and the exponent of an exponential function is the variable. If you switch those two and you have the base be a variable and the exponent a constant, we call that a power function, like x squared, x cubed, x to the square root of 2 power, right? Any quantity that changes by a constant factor over time or distance or whatever is described by an exponential function. So what does that mean? A constant factor means there's some constant that you could keep multiplying it by. So say that your population doubles every 50 years, okay? Then after 50 years, you have double the population. After another 50 years, you'd have to multiply your previous population by 2. And then after another 50 years, you'd have to multiply it by 2 again. So there's this factor 2 that you keep multiplying by. And that would be your base, A, 2, in that description. So anyway, the graph looks like this. This is if a is larger than 1. In other words, it's in the intervals 1 to infinity that you see up here. Right? Still can't get used to this pointer. If a is in here, it looks like this. We call this exponential growth, because you always read left to right. It's growing. Our current virus problem is unfortunately following a curve similar to this as far as number of people getting infected, and also a number of people already infected follows a similar curve. Okay, that's if a is larger than 0. Notice there's an asymptote that's on the x-axis, That's for this basic one. Now, of course, we can put a coefficient on in front of it. We can put a coefficient on the x. We can add or subtract something from the x. And we can add or subtract something from the whole thing. And what these things do is make this a little steeper, a little less steep, or that's the coefficient. And these other things can, well, adding or subtracting something from x, or adding or subtracting something from the whole thing, which is y, just shifts the graph around. Okay, but this is the basic one, which is like this. And it looks the same regardless of what a is. It always goes through this y-intercept of 1. The basic one does. It has an asymptote here. So it's pretty easy to graph. It's not like a parabola where you need to know the vertex. And this is what it looks like if a is between 0 and 1. That's called exponential decay. So I like looking at these things where the base could be the two different types. I like looking at them this way because it makes it really obvious. You know, there's two types. This type is exponential decay if a is in here. And this type here is exponential growth. You know, it's just nice and visual, right? So, decay. So we call this over here the tail of the exponential function, where it approaches the asymptote. So exponential decay has its tail on the right, and exponential growth has a tail on the left. I think I might have just written this out. Nope. Notice that exponential functions are 1-to-1. They pass the horizontal line test, right? So that means that their inverses are functions. So they have inverse functions. And the inverse functions we call logarithms. And we'll deal with logarithms, I think it's the very next section. Those are just the inverses of these. And so the graphs are going to look pretty similar, just reflected in the xy axes, you know, vertical asymptote on like that. Okay, so that's it for that first video.